Well, good day, everybody, and let us get back to it here. And we're in our unit over solutions and equilibrium, and now we want to jump into the concept of equilibrium. So let us consider this reaction. I have silver cations aqueous reacting with two molecules of ammonia aqueous, yielding diamine silver aqueous, and that's what we call a complex ion. We don't have to worry that it's a complex ion. All we have to worry about is this reaction. And the question is, what must be true for this reaction to be at equilibrium? Okay, I think we have some new stuff to learn here. So let's go to our concept map and let's talk about equilibrium. That's a big word. Equilibrium. And let's start off with our definition of equilibrium. Well, I'm going to give you two. The first one is a steady state in a reversible reaction in which the concentrations of the reactants and products are constant. Okay, are constant. So that is one definition. It's a steady state. That means the situation is not changing. In a reversible reaction is reversible, and the concentrations of my reactants and products, and remember, when we're talking concentrations here, most commonly we're talking about molarity, right? Which are moles of my solute per liters of solution, are constant. Now be careful here. This does not mean that the concentration of my reactants equals the concentration of my products. No, I'm not saying that. That is not necessarily true. All I'm saying is that my concentration of reactants is constant, meaning it's not changing, and the concentration of my products is constant, meaning they're not changing. Doesn't mean they're equal. It just means that they are not changing. Now, does this mean that the reaction has stopped? Not at all. The reaction is occurring in both directions. Reversible. I guess maybe we need to talk about what's reversible mean. Reversible means I have a reaction going in one direction and a reaction that goes back in the reverse. So let's take something like, how about nitrous acid plus water will form something we call hydronium plus nitrite. And so what does this mean? This means that nitrous acid and water will react going in that direction to form hydronium and nitrite. But also, nitrite reacts with hydronium and goes back in the other direction to form water and nitrous acid. So that's what we call a reversible reaction, meaning the reaction could go from left to right, yoink, and it can go from right to left, doink. And so that is a reversible reaction. Now, another definition I like is this is a situation, situation for a reversible reaction in which the rate of the forward reaction equals the rate of the reverse reaction. Okay? Now, this definition will help us more when we learn kinetics, but for the time being, we can think of a rate of the reaction, meaning, hey, that's the change in concentration per time. So when I say, what is the rate of reaction of the forward, that means how do my reactants change per time, left to right, and then the reverse reaction would be how do my reactants, concentration of my reactants from the right side to the left change per time. So these are the two definitions that I like for equilibrium. Good. And they both have a couple things in common, right? And let's go to them. What must be true? Well, the first thing that must be true is what? I must have a reversible reaction. Must have a reversible reaction. Second thing that must be true is that and we can say this two ways, either my forward rate, the rate of the forward reaction, must equal the rate of the reverse reaction. Okay, so that means the rate at which silver cations are reacting with ammonia to form my diamine silver complex is equal to the rate at which my diamine silver complex is breaking down into ammonia and silver. So we could say that this arrow represents my forward reaction and this equals my reverse reaction. Okay? Or another way to say this would be what? The other thing that must be true, let's put an or to, that the concentration of my Ag plus ammonia and diamine silver, diamine silver is constant. So those are the two conditions. I have to have a reversible reaction and I have to have my forward rate equaling my reverse rate. Good? Moving on. So let us consider this reaction again. And we want to know, what is the expression for KEQ? Yikes. What is KEQ for this reaction? Okay, so we need to know a little bit more. What a mess I've created here. Zoink. No, 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 no. No, 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 no. Let's come down here and let's talk about KEQ, which some people will call, or AKA, also known as KC. KEQ, KC. Good. So what are KEQ, KC? These are things we call our equilibrium constant. Our equilibrium constant. And for every reaction at equilibrium, and I really have to say what? Reversible reaction at equilibrium, there is an equilibrium constant. Jawohl. Yes. So every time I have a reaction at equilibrium, there's an equilibrium constant. Now, what is that equilibrium constant? Well, let me show you the expression for my equilibrium constant. Okay. So let's take A to the A, and we're called aqueous, plus B to the B, aqueous, is in equilibrium with C to the C, aqueous, plus D to the D, aqueous. Okay, so let's say I have that reaction. My KEQ for this reaction is going to be equal to the concentration of my products raised to their coefficients. So the concentration of my C raised to the C times the concentration of my D raised to the D over the concentration of A to the A divided by the concentration of B to the B. So that is the definition, I guess I'd call it a definition, for the expression for KEQ. Now, what's important here is KEQ only includes gases and solutions. Okay, that means we never put solids or liquids in the KEQ expression. Okay. Cool. All right, so KEQ is equal to concentration of my products raised to their coefficients in the balanced equation over the concentration of the reactants raised to their coefficients. All right? Good. So let us try to figure this out. Here we go. We want the expression for KEQ, and I have here, these are my reactants, right? My reactants. Here are my products. Good. Okay, so these are all aqueous. So since they're all aqueous, they show up in my KEQ. I want to take my product raised to its coefficient. So I'm going to take the concentration of, and I'm going to have double brackets here, the concentration of my Ag NH3 2 plus, whenever I have a complex, they're also in brackets. That's why that's in brackets already. Okay, and what's my coefficient here? It's a 1, so it's raised to the 1 over concentration of my silver cation times the concentration of my ammonia, what? Squared. There we go. That's my KEQ. Great. If the equilibrium constant is 1.7 times 10 to the 7th, do the reactants or products predominate at equilibrium? Yipes, predominate. Okay, let's go back and let's fill in some more information. We're still talking about our KEQ, and let's talk about the meaning. The meaning of KEQ. Okay, so the KEQ tells us a little bit about the concentrations, right? It tells us about the concentrations, something about the concentrations at equilibrium. And I guess I should be careful here, right? I really should have put an E underneath all of these because these represent equilibrium concentrations. So this tells us about the concentrations at equilibrium. Now, these guys we said are my products. These guys I said are my reactants, right? On the left side, and these guys on the left side, these guys are on the right side. If I have a really big number, let's say KEQ is really big, so let's say KEQ is much, much bigger than 1. So if KEQ is much, much bigger than 1, what must be true? Well, that means my numerator is much, much bigger than my denominator. Well, my numerator is what? My products. So that would imply that the concentration of my products is much greater than the concentration of my reactants. Good. Well, if the concentrations of my products are much greater than my reactants, well, what predominates when I'm at equilibrium? Meaning, what is more prevalent, the products or the reactants? Well, certainly, if the products are much, much greater than the reactants, the concentration that is, then the products predominate at equilibrium. And all I mean by predominate, it means there's a lot more. So there are a lot more products at equilibrium than there are reactants at equilibrium. What if my KEQ is much, much less than 1? Well, if it's much, much less than 1, let's go back up here. Let's assume this is, let's change colors too. Let's assume this is much less than 1. How does that become so much smaller? Well, that means my denominator is much bigger than the numerator. Well, what is my denominator? My denominator are the reactants. So that means, yoink, 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 that my concentration of reactants is much, much greater than the concentration of products. Yahoo! And so that means what? At equilibrium, my reactants predominate. Predominate at, oh my gosh, why do I have to keep spelling this? Equilibrium. Wow, hooked on chemistry phonics, right? Good. Here we go. So what do we have here? 1.7 times 10 to the 7th. That's a really big number. That means my KEQ, what? That means these guys are much bigger than these guys. For this guy to be much bigger, that means I have to have a whole bunch more of this than these guys. So that means what predominates? My products predominate Predominate. All right, cool. All right, I think you guys can do the next one. And I won't say all right anymore today. All right, good, cool. Bring me back when you have this. Well, we want to be careful here. What's the expression for KEQ? We said, hey, we want to look at KEQ is equal to the products to their power, I'll call it N, over reactants, whatever they are, to their power, we'll call that M, right? But we said be careful. This is only for aqueous and gases, not solids or liquids. So look at here, I have a solid, so we would not put that into our KEQ. So our KEQ is equal to concentration of my carbonate raised to its power times the concentration of my silver raised to its coefficient. There we go. What goes in the denominator? Well, nothing. 1, right? So we wouldn't even have to put that. So my KEQ is equal to the concentration of carbonate times the concentration of my silver ion squared. All right. If the KEQ is 8 times 10 to the minus 12th. Wow, that is a really what? Small number. That means this KEQ is much, much less than 1. Do the reactants or products predominate? Well, if my KEQ is much, much less than 1, then that means these guys must be very, what? Small. And if they're very small, that must mean what? My reactants predominate. And what this means for me is when I put some silver carbonate in some water, most of the silver carbonate does not break into, does not break into the ions, but most of it stays solid, meaning I would have a very, very low what? Solubility. There we go. All right. That's our intro to equilibrium. I think it's time for us to call it a break, and next time we will talk about Le Chatelier's principle. Ciao.